and for the rest of the quarter, because we have, including today, we have a total of 5 lectures left. We probably don't have enough time to finish or to go to solution, and I don't want to rush it through. So here's our plan. Today we'll finish our discussion on chapter 6, which is the equilibria shifting for ideal gas mixtures and reactions. And we will get started by talking about degrees of freedom and introducing chapter 7. And on Friday, Professor Abby Kovner will be here for 30 minutes to go over the one component phase diagram with you, just one topic, that's a 7.2. Then your TA Qing Yang will be here to record Professor Abby Kovner's lecture, and he will also be with you to go over some practice problems on ideal gas equilibria. So that's Friday. Now, next Monday, we will finish chapter 7. Again, phase diagram, the Clapeyron equation, and we will cut it after the Clapeyron equation. We'll not go to higher order like phase diagram or the solid-solid phase transfer. We'll just cut at the Clapeyron equation. Know how to use the Clapeyron equation and the phase diagram. So we'll cover that next Monday or Wednesday, depending on how fast we go. And on Wednesday and Friday, it's all going to be review. So we're going to do 2 things. One thing is to go over all the topics and to finally demonstrate to you this is still a chemistry class. I know it is very mathy. I know we have lots of derivation, but it's still a chemistry class. And then we will have basically do 2 comprehensive problems together. When I say comprehensive, okay, so rewind. We'll do 1 set of multiple choice true and false problems together and 1 set of comprehensive calculation, plug-in, derivation problems together. So that's our goal for the rest of the quarter. So you know what to expect. I will also upload those lecture notes later on when it's available. I have also finished a walkthrough for your midterm 2 exam. I'll post it later today. And because I post my walkthrough a bit late, I'll extend the regrade period to the end of tomorrow. I think it was end of tomorrow, right? Okay, so end of tomorrow is fine. Okay, I saw this end of today for some reason. Nevertheless, you have end of tomorrow to submit your regrade request on Gradescope. Okay, do we have any questions for the administrative things? No? We're doing good? Okay, so at the end of our last lecture, we already started talking about shifts in ideal gas reaction equilibria. So this is a good point for you to practice your skill in can I make that link quickly if I see this kind of problem in a multiple choice problem? Can I solve this problem within like 2 minutes or 3 minutes without doing any calculation? So again, at the heart of predicting the shifts in equilibrium reaction equilibria, what we have is you're comparing the reaction quotient and the equilibrium constant, right? So at equilibrium, your reaction quotient will equal to equilibrium constant. Now, when you have reaction quotient smaller than equilibrium constant, you have forward reaction. Where you have equilibrium reaction quotient larger than your equilibrium constant, you have backward reaction. Some of the things we went over. So for example, when we say the equilibrium constant, this one only depends on temperature. So when we're looking at a scenario where the temperature is not changing, you have the isothermal change of pressure or volume. What we're looking at is how your reaction quotient is changing with respect to that, right? But if we're keeping our pressure or volume constant changing the temperature, then we're talking about how your equilibrium constant is going to shift. So we see several examples together. So at the beginning, we talk about the isobaric temperature change. So that means isobaric temperature change means we are not changing the pressure, so your reaction quotient remains the same. We're changing the temperature, so your equilibrium constant is shifting depending on how the temperature is changed. We went over a derivation here to say like we start from the Ventov equation, and doing a bunch of calculus, we find out how your equilibrium constant is going to change with respect to temperature. right? And depending on whether this one is a positive number or a negative number, we're predicting your equilibrium constant to change differently. So in this case, your equilibrium constant, gas constant, temperature square will always be positive. So whether this differential is a positive or a negative number only depends on the nature of your reaction. Whether it is endothermic, means you have a positive delta H, your reaction absorbs heat, and you have the equilibrium movement accordingly. Or if you have an exothermic reaction, you have a negative delta H, so this derivative becomes negative. So when temperature increase, your equilibrium constant decrease. And with your reaction quotient stay the same, you can predict how your reaction is going to move with respect to temperature change. Okay, next up, we talk about the isothermal pressure change. So again, like what we said, for isothermal pressure change, we're saying, hey, it's isothermal, so your equilibrium constant will remain unchanged because temperature is not changing. So in this case, we're just looking at the pressure change and how does your partial pressure change and the reaction quotient change accordingly. So we end up having the expression here that your reaction quotient, so at equilibrium, that's your reaction quotient. And after the pressure change, basically we're saying these pressure have been changed inside that bracket. All right, so inside the bracket is the same. So how your reaction quotient change depends on the stoichiometric coefficient here. So which one has a larger stoichiometric coefficient? And in this case, we end up with a conclusion that an increase in pressure at constant temperature in a closed system will shift the equilibrium to the direction in which the system volume decreases. And this is also where we come to play that when we say the stoichiometric coefficient here, you only care about stoichiometric coefficient for gas molecules because your liquid and solid volume are not sensitive to the pressure change. All right, so this is a quick review on what we discussed already. And we have a few more rules to talk about. The first one is called the isochoric addition of inert gas at constant temperature and volume. So a few things. First thing, when we say it's at constant temperature, you should instantaneously write your equilibrium constant is not changing. Right. And for ideal gases, we can write our partial pressure equals to number of mole Ni of that species, RT over V. So adding the inert gas to a mixture, assuming ideal, will not change your specific ingredient in there. For ideal gases, right? We don't care about how many molecules are there. We only care about their partial pressure. So your partial pressure remains unchanged with the addition of inert gases. So in here, these I abbreviates for, these are the ingredient involved in that chemical reaction of interest. So that tells us my QP, or my reaction quotient, which equals to the product of your partial pressure to the power of your stoichiometric coefficient, will be unchanged. Now, that means for a system at equilibrium, adding inert gases to that system will not shift its equilibrium. It will remain at equilibrium, so no effects. Right. And the next topic is a little bit more complicated. So we're getting to the Le Chantelier principle, but in a more thorough way to re-emphasize the Le Chantelier principle different from GenChem. So this part, we're talking about addition of reactant gas or product gas, if you like. Now imagine you have a reaction between A to B that's in equilibrium with 2C and D. So adding substrate A to this mixture, how does my equilibrium shift? So the GenChem version of the Le Chantelier principle will be like at constant T, Well, you have your Kp unchanged. And if we calculate for our partial pressure, so Pi equals to, again, Ni times RT over V. So your partial pressure for your B, C, and D will not change. Right, because we're not adding any of these ingredients to my mixture. For reactant A, we have that equals to Na times RT over V. So we're adding Na, so your number of mole of your molecule A increase, and consequently the partial pressure of your A will also increase. Now your total reaction quotient equals to Pc squared, that's your coefficient there, times Pd, and divided by Pa -1 and Pb -1. So with your Pa increase, what we have is your Qp is going to decrease. So we're predicting a Qp smaller than Kp. And what kind of reaction we have there? Which direction is it going forward, right? So what do we mean by these principles might not be universally applicable? Like, don't go too fast jumping to the conclusion, because we have exceptions here. So let's come to this point. So back here, this one we're talking about constant temperature and volume. So this one is okay. It's generally applicable because we're talking about constant volume. So your partial pressure is always equal to the number of mole. So this principle stays true. So generally true for constant temperature and volume processes. But when we move on to constant temperature and pressure scenarios, then there might be exceptions. So let's see how that works out. So now we're talking about constant temperature and pressure. So again, for constant temperature, let's just write your Kp is not changing. And what we have is your partial pressure. Now we have constant pressure. So in order to calculate for partial pressure, you have the mole fraction times the total pressure. Now, when we're talking about mole fraction and the total pressure, then the number of mole of your ingredient might not directly proportional to the mole fraction change. So what does that mean? So let's look at an example together. So when we see the movement here, what we have is, let's use our ammonia production example again. We're saying the equilibrium has reached at some random temperature and pressure. So we can write out our equilibrium constant. So K equals to, I say K chi, so that's the mole fraction version of your equilibrium constant. That's your chi for NH3 at equilibrium to its stoichiometric, to the power of its stoichiometric coefficient over chi N2 equilibrium and chi H2 equilibrium to its power of third. On the right-hand side, you have the mole fraction version of your reaction quotient. It's pretty much the same idea. It's just a product of your NH3 at any point over the mole fraction of your N2 times the mole fraction of your H2 to the third. Okay. Now let's look at some special situation. Assume we know that at the equilibrium, you have 1 mole of NH3, 3 mole of N2, and 1 mole of H2. So that means you can calculate your chi NH3 equals to 1 to the 5 equals to 0.2, chi N2 equals to 0.6, and chi H2 equals to 0.2. So this tells me we have our equilibrium constant equals to 0.2 squared divided by 0.6 times 0.2 third. That's about 1.667. That's your equilibrium constant. Now imagine the situation. We now added 0.1 more of your N2 to the reaction mixture. So adding 1.1 more of N2 to the reaction, you're expecting you're expecting we're adding the reactant, so we're pushing the reaction to the other way, right? So what we have here is adding the reactant. We're expecting pushing the reaction to the forward direction, and what we have, you can calculate for your mole fraction, chi NH3 equals to 1 over 5.1. That's 0.196. And chi N2, that's 3.1 over 5.1 equals to 0.608. And chi H2, that's 1 over 5.1 again, that's 0.196. And Qx thus becomes 0.196 over 0.608 times 0.196 over 3. We do that calculation to get 1.645. So we have our reaction quotient smaller than our, I have a feeling that I did this example wrong because it was supposed to prove that in some special situation, it's actually going to the backward reaction, but let me double think. Yeah, I might have do this example wrong. So yeah.
Would the 0.196 be squared?
Yes, this one is squared. No, it's not the calculation that I did wrong. I think I should be adding the NH3 and prove it the other way. But nevertheless, I'll post a recording later on to rephrase what I said here. What I want to prove, so what my point the point I'm trying to prove is at some special situation, adding the product will actually shift your reaction forward as well. But I don't think this is a good example. I'll fix that example with an additional recording later on. Sorry about that. But the point here is we want to rephrase our Le Chantelier's principle. It's that when we're saying the system is at equilibrium, the change in one of the intensive variables that determine the equilibrium will shift the equilibrium in the direction, counteracting that change in the variable. So the difference here is instead of the original Le Chantelier's principle, you're talking about addition of your reactant or addition of your product in number of mole, which is an extensive property. So just keep in mind, when using the Le Chantelier principle, you should be talking about an intensive property. So instead of the number of mole, we should be talking about mole fractions. So in special cases where even if your number of mole is increasing, but the mole fraction is decreasing, then you might have a different behavior than your GenChem version of the Le Chantelier principle. And I'll fix that example to show it to you later on. Okay, any questions? Sorry for the confusion. Nope? Okay. So next up is one of your example problems here. So that's the 6.48. So the point here is we're gonna do, so the question said we have an ideal gas reaction where you have one gas molecule go to like two different gas molecules. And can you quickly predict how that equilibrium is gonna shift to the right, to the left, or not gonna change anything? All right, so this one is basically using whatever we discussed and quickly come to a conclusion, like whether or not your equilibrium is gonna shift which direction it's going to shift. So first one, temperature is decreased at constant P. So temperature decrease and constant P. So this one, we have constant P. Now your partial derivative equals to chi I times constant P. So your partial derivative is not changing. So that tells me that for my first scenario, my Q will remain the same. The reaction quotients remain the same. And for this reaction, you have temperature is decreased. So we're talking about the temperature is decreasing. But we don't know how your equilibrium constant is going to change with respect to temperature. So in this case, again, what we have is dkp naught over dt equals to kp naught times delta H over RT squared, right? So this derivative will have the same sign as your delta H naught. And delta H naught you can calculate using the appendix data of your delta H of formation of your reactant and product. So you can calculate this number, find out what is your delta H of the reaction, and then predict how that equilibrium is going to shift. So in this case, I'm going to give you the number. This one is a positive number. And when we have a positive number, we say this derivative is positive. So your Kp naught will increase with the temperature increase, or this will decrease with the temperature decrease. And that tells me my equilibrium constant has become smaller. So your reaction quotient is now larger than your equilibrium constant. Reaction shifts back. Okay, next up, volume decrease at constant temperature. So constant temperature, so your Kp is not changing. We're talking about how your reaction quotient is going to change. So in this case, when we are talking about volume, total volume is decreasing, we are looking at, let's see, put it down here. Pi equals to Ni times RT over V. So what that means is all of your Pi will equally increase or proportionally increase with your volume decrease. Now your reaction quotient equals to the product of your partial pressure to the power of the stoichiometric coefficient. So you count the number of gas in the stoichiometric coefficient. We start from one gas molecule, we end up having two gas molecules. So what that means is your product is more sensitive to that partial pressure increasing, or your reaction quotient is going to increase with your equilibrium, will increase with this volume decrease. And thus your reaction quotient becomes larger than your equilibrium constant. So this just goes on, and I have the walkthrough posted on the annotated note. Do it yourself and try to get those calculations, or not calculations, but get those connections checked. Okay. Any questions? No? Okay. We're then moving on to our next lecture, which is 17. So this one is a relatively short one because I'm only covering the 7.1, and Dr. Abby Kovner will come in to talk to you, to lecture on the one component phase equilibrium. So before we talk about phase diagram, we have a few review items, which are definition of terms. So what exactly is a phase? So this is go back all the way to lecture 1. So remember, the definition of a phase is a homogeneous portion of a system. A system might have multiple phases. Typically, it can have multiple solid phase, So when we say multiple solid phase, means their crystal structure is different, it's topologically different, and those solid phase can be in equilibrium with each other. It can have several liquid phase, like water and oil, they're not like miscible with each other, but usually only one gas phase is available. Now, these are the example we've seen before. So for example, you have a cup of still water, not considering the vapor, it is homogeneous. And if you have ice water, then it's heterogeneous. You have a solid phase and your liquid phase. There's a two-component heterogeneous system with two phases. Now, if you are talking about the ice soda water, then you have three phases. That's not considering the water vapor. Okay. So the purpose here of 7.1 is the phase rule. So this tells you the number of degree of freedom or variance F of an equilibrium system. So in this case, what's the definition of our degrees of freedom? So what we're saying is the degrees of freedom F tells you the number of intensive variable needed to specify its intensive state. So here are some of the examples of your intensive variables, if you can think about. You have pressure, temperature, mole fraction, or chemical potential. Right, so these are all intensive properties. And remember, when we say intensive properties, these are the properties that doesn't care about how big it is. Like a cup of water, right? The density of 1 cup of water and the density of a ton of water is the same. So density is one of your intensive property. Now, extensive properties, you have volume, you have Gibbs free energy, you have internal energy. So those are extensive properties. So when we're saying number of intensive variables needed to specify its intensive state, what we're saying is when we're saying, say, a cup of water, a cup of ice water, that's in equilibrium. The ice and water are in equilibrium with each other. Now, when you have a bunch of ice water, it's the same idea. We're using the same kind of intensive property to describe the intensive state. Whether you have 1 cup or 100 cups of water, they will remain the same. So we will do a quick derivation on the phase rule based on 2 assumptions today. And we'll drop these assumptions later on to make the phase rule generally applicable. So we'll start from simple, and then we'll drop our assumptions later on. So the 2 assumptions we're making is, first of all, no chemical reactions can occur. Secondly, we're saying every chemical species will be present in every phase. So with that in hand, we're talking about C abbreviates the number of different chemical species in each phase. And P is the number of phase present. So back to our cup of water example, if we're talking about the number of chemical species, we only have 1 chemical species, which is water, right? And that take consideration of 3 phases. If I take consideration of the water vapor, otherwise it's 2 phases. So when your water is present in different kind of phases, we count that as 1 component. All right, so with both of our assumptions, what are our total mole fractions that are available? We're talking about intensive properties, right? On top of temperature and pressure, we have mole fractions that describes the composition of that mixture. So how many total mole fractions do we have? Now, what we have, for example, in case we are talking about 2 chemical species, oxygen and nitrogen in gas and liquid phase. So in gas phase, you have chi of oxygen gas, you have chi of N2 gas. In liquid phase, you have chi oxygen in liquid and chi nitrogen in liquid. So the total mole fraction, for example, will be 2 times 2. Or you can write it more generally as your phase times the component. Right, so that's the total number of possible mole fractions. So the PC. So, is that the end of the story? Because once we know the number of mole of every species in each of the phases, we are already defining that mixture, right? So that means, is this true that your variation just equals to your total number of possible mole fractions combined together, and plus your temperature and pressure? So this 2 is your T and P. So that gives you the mechanical and thermal equilibrium. Now, in this case, we don't necessarily need our P times C number because your mole fractions are not all independent from each other. So there are degrees of freedom that we need to reduce because of your mole fractions are connected to each other. So there are two different types of relations we need to take consideration. All right, so this is where we start. And the question here is, how does my mole fractions connect to each other? We have two different things to take consideration. The first thing is for every phase, so inside every phase, your mole fraction must add up to be 1.
It's not user, right? I didn't show you one of the signs that's actually not. It's not user.
Okay, I have to shout very loud. I don't know where that comes from. Okay, nevertheless, so we are talking about the sum of all your mole fraction in each phase will add up to be 1. Or maybe I can just remove it. Okay. Let me just. Is it?
Is it on the computer?
No.
Because it sounds like my professor.
Oh, well, maybe they forgot to turn their mic off. Nevertheless, so I muted the room. Should be fine. So we have two different kind of relations to take consideration. First of all, in each phases, your mole fraction must add up to be 1. It's a fraction, so that's naturally saying, like for all your species C, for every species C, for the phase alpha, your all species must add up to be 1. So that means for the number of phase we have, for every phase, we can eliminate 1 degree of freedom because your mole fraction adds up to be 1. Or what we say is because of this relation, we eliminate P degree of freedom. So P is the number of phase. All right, with me so far? Just picture like you have in every phase, your number of mole of every chemical species adds up to be 1. Simple enough. Next up, we have equilibrium condition come to play. So when we look at a mixture that is in phase equilibrium with each other, like a cup of ice water, right? Your ice and water are in phase equilibrium with each other. So that means we have phase equilibrium. So remember, when we have phase equilibrium, what we are saying is the chemical potential of your specific chemical, 1, is in equilibrium with all phases, alpha, beta, and gamma, etc., etc. All right? So for a system in equilibrium, in phase equilibrium, like a cup of ice water, your solid water and your liquid water are in equilibrium with each other. So the chemical potential of your water in solid phase and liquid phase will be in equilibrium with each other. So in this case, if we generalize this observation, we have for every chemical species, it is in equilibrium with different kind of phases, right? So you have chemical species times P minus 1, degree of freedom be minus. With me so far? So taking these two connections into consideration, what we have. Now our total degree of freedom, we start from PC plus 2. So this one is assuming all your mole fractions are independent from each other. Plus 2, that's your temperature and pressure. We minus P, so that comes from your mole fraction adds up to be 1 in every phase. and minus C times P minus 1. So that's a phase equilibrium for every chemical species C. So this can be further simplified, obviously. You write it out. You have PC plus 2 minus P minus PC plus C. So the PC term cancel out. We have F equals to C minus P plus 2. Assume there's no reactions. So this is the generalized phase rule under our two assumptions. What does this phase rule mean? It tells you that once this F degree of freedom is reached, the value of all other intensive properties of each phase will be fixed. All right, so imagine a scenario. You have a one component system, like just water, but you have three different phases of water in equilibrium with each other. What do we have? So what we have here, C is 1, we only have water, minus three different phases, like liquid, solid, and gas phase in equilibrium with each other. That's 3, plus the temperature and pressure. So this gives you 0. So that tells us one thing, is for all water, chemical species, water, or any one component species, there only exists one point that your liquid, solid, and gas are in equilibrium with each other. It's a very specific point that we call triple point. You'll see that in the phase diagram. All right. But continue our discussion. So here we have, again, we still have our two assumptions in play when we look at this form of our variation or degree of freedom. Let's see how can we make this phase rule more generally applicable and drop those two assumptions. So here are the things. First, let's drop the assumption 2, that's saying every chemical species is present in every phase. This one is actually pretty straightforward. Just bear with me with logic. So when we say now, instead of having your chemical species in every phase, let's just remove it randomly from one of the random phase delta here. Now the number of intensive variable is reduced by 1, but the number of relation between variable is also reduced by 1. What does that mean? So let's look at an example. We have a saturated aqueous salt solution with pure salt, solid salt. So in this case, in the solid phase, what we have is, let's say, NaCl solid. And in your solution phase, we have NaCl aqueous and H2O. Or it should be liquid, I guess. Now, in your solid phase, what we have is your chi H2O solid equals to 0. And also your chi NaCl solid equals to 1. Now, this one no longer is a variable because we don't have water in that solid phase. So the intensive variable is reduced by 1. All right, so this is no longer an intensive variable. Now, when water is absent from that phase, we're reducing one intensive variable. What about the relations? When water is not present in the solid phase, this relation, which is the equilibrium between your solid water and your liquid water, is also broken. Right, so this one is -1 relation. And on the top one, that's -1 variable. So this is just one of the examples to demonstrate that you don't necessarily need to have your chemical species present in every phases. And this F equals to C minus P plus 2 will still holds true when some of your species do not appear in every phase. Still no reaction, but we don't care if you have that species in every phase. okay? So some of the example we can do is, for example, we give you a specific system and ask you to find the degree of freedom considering a liquid solution of methanol and ethanol in equilibrium with a vapor mixture of methanol and ethanol. And also ask you to give a reasonable choice of the independent intensive properties. So in here, we have our phase rule. There's no reaction taking place. So we have C equals to 2. That's your methanol and ethanol. P equals to 2. That's your liquid solution and the vapor. And, well, in this case, we can calculate F equals to 2. And in here, you want to think about what are the reasonable choices for independent intensive variables. So that means, first of all, we need to have one component that tells you about the thermal and mechanical equilibrium. So here, T or P. And you want to know in that liquid, what is the mole fraction? So it tells you that chi liquid. So obviously a choice of like the mole fraction of liquid methanol and the liquid ethanol doesn't work because they're dependent on each other. One thing you might want to think about is why you can't choose temperature and pressure for this question, or why we're not choosing temperature and the vapor mole fraction of your ethanol. So think about that while we work on it. That's related to some of our previous discussion on the ideal gas mixtures and so on. All right. Then the last bit of information is how do we drop that assumption 1, where we're saying there's no chemical reactions taking place. So chemical reactions will further reduce the degrees of freedom that we have discussed before. So it reduces degrees of freedom by several ways. The first way is a more general way. So whenever you have independent chemical reactions, so that's just a random independent chemical reaction. Now there exists a equilibrium condition. So for every independent chemical reaction, you have one equilibrium condition that link your chemical potentials together. Your chemical potentials are your intensive properties of interest. So what that tells us is every independent reaction eliminates one variable from your total degrees of freedom. Just think it through. Like you have every time we are eliminating or building a connection between your intensive properties, we're eliminating 1 degree of freedom. So when we have independent chemical reactions, when we say independent chemical reactions, what we are saying is at equilibrium, the sum of these chemical potentials equal to 0. So that's 1 less degree of freedom. All right, and we abbreviate these independent reaction using a small letter R, stands for reaction. So your total degree of freedom now becomes C minus P plus 2 minus R. And on top of the independent chemical reactions, we have other factors that are system specific. So these are the things you have to look at one by one. So for example, if we have an equilibrium in a closed system that only contains NH3, so that's where we begin. We add a catalyst so that this reaction can take place. All right, and what we're saying is that if the system starts with only NH3, then all your nitrogen and hydrogen are being produced because of the decomposition of NH3. So we have an additional constraint between your intensive variables. Like, for example, your mole fraction of H2 will always equals to 3 times the mole fraction of N2. So for every molecule of N2 produced, 3 more of your hydrogen is being produced. So that's a stoichiometric relation, or 1 degree of freedom that's being added. And we call it A. There are other types of system-specific restrictions. So for example, if you dissolve like sodium chloride in a cup of water, and you have your Na plus and Cl minus dissolved in that cup of water, it's fully dissociated. So the number of mole of your Na plus must equal to number of mole of Cl minus, or the mole fraction of Na plus must equals to mole fraction of Cl minus. That's another example of the additional variable that can be reduced. Or if you're looking at a aqueous solution that has some kind of cation, some kind of anion in there, now the charge must be balanced. That's another degree of variation to think about. So these are system-specific restrictions. Practice on the chapter end problem will help a lot to quickly get what that A is. All right. So our phase rule now becomes C minus P plus 2 minus R minus A. And going down here, this is our general phase rule. Again, knowing what each component is. Now, C stands for your component. P stands for your phases. This 2 here is your temperature and pressure. R here is your independent reaction. And again, when we say independent reaction, you can't have a sequential reaction that can add up to an overall reaction, right? They must be independent from each other. And A is your system specific. And in textbook, in some of other textbook, people also define the C, I, and D as C minus R minus A. So this means independent component. And in this case, we have F equals to C, I, and D minus P plus 2. And in this case, because we use that phase equilibrium between the same chemical species, you cannot have walls to separate those phases from each other. Otherwise, that doesn't count as a connection. And we have like PV work only. Closed system. Yes?
What's the degrees of freedom for one of the independent components?
No, so the degree of freedom is describing the entire system.
But when we use the C independent.
C independent is the component minus reactant, like number of independent reactions, and minus additional connections. So let's do one example together. We're running out of time, but we'll quickly do this example together. So let's say we have an aqueous solution of HCN and KCN. So in there, the algorithm to go is first write all the possible components. So we have H2O, we have H plus, we have Cn minus, we have K plus, you have your HCN, right? And in this case, you have your total number of component equals to 1, 2, 3, 4, 5. And the number of equilibrium reactions involved is HCN in equilibrium with H plus and Cn minus. Now, I don't have the KCN dissociation because that process is not equilibrium. You can also write it in, it doesn't change anything. So here you have your reaction equals to 1. what are the additional constraints? Now your charge must be balanced. So what that means is the total number of H plus and K plus. So these are my cations, must equal to the number of mole of your Cn minus. So that gives you A equals to 1. All right. And your total independent component equals to C minus R minus A. That's 5 minus 1 minus 1. And that gives you 3. And using the phase rule, you have F equals to C int minus P plus 2. So in this case, we only have one phase that is an aqueous solution. So that means we have 3 minus 1 plus 2 equals to 4. So try that out with the other examples. You have the answer key there. I'll be around to take questions. And I have one more example there. So that's talking about when scenarios you don't have that species in different phases, and try that out yourself. Yeah. Well, you can add it and find out if it can change. So you're adding this, but at the same time you're adding.
You're gonna take away.
No worries.